So, in the previous lecture we came across the Navier-Stokes equation, and eventually after making assumptions of a Newtonian constitutive relation and also considering the fact that we are interested in an incompressible system. This is the Navier-Stokes equations that we have obtained, that is to be used together with the mass conservation statement or the equation of continuity, in which in this particular case of an incompressible flow, this translates to the fact that I have the velocity divergence being 0, and then a relation between the pressure gradient, the viscous term, body force, which is balanced by the fluid acceleration. Now, this equation we are basically, what we said in the previous lecture is that it describes all kinds of fluid motion within the assumptions that we have made, the kind of fluid that we have in mind. So, excuse me. So, regarding everything that we see around pretty much is described by these sets of equations. Now, we will do this a little bit more formally in a few lectures, but right now if you stare at what is there on your left hand side of the equation and what is there on the right hand side of the equation. So, on the right hand side of the equation you have this term which is the viscous term, the term which is basically the Laplacian of the velocity field, and on the left hand side you have this particular term which is the mass times acceleration per unit volume, or rho times the acceleration. So, there are different limits which one could study while doing this kind of problems. So, one particular limit, so as I said, we will give a formal name to this. So, one particular limit could be where your viscous effects are insignificant when compared to your inertial forces. So, dissipation is not something that is very important, in which case that equation reduces to the following form, where I ignore the frictional effects in the fluid and treat this as an equation which is an equation that is describing an inviscid flow, or the equation is known as Euler's equation. So, Euler's equation just gives us that rho times the acceleration is balanced by a pressure gradient and body force that is there. There are no viscous effects that are there in this particular problem. The other regime where your inertial forces are insignificant when compared to your viscous forces would be where I drop the entire LHS and I have the right hand side as the object of interest. So, this equation is a very strongly dissipative or viscous equation, and this equation is known as the Stokes equation. So, from that Navier-Stokes equation that we have derived, we basically arrive at these two limiting cases. In one case you say that viscous effects are not so important, and you deal with an equation which is also in some cases labeled as describing an ideal fluid. An ideal fluid being where there are no frictional effects that are there. So, there is no viscous contribution to your momentum balance. So, that is your Euler's equation. And the second limit is where you are saying that the fluid does not have any acceleration. There is zero acceleration in the fluid. So, whatever is the applied external force in the problem, that is basically balanced by pressure gradient and viscous diffusion. Now, these two limits are often studied quite a lot. We will be actually studying the first limit, which is the Euler's equation. This would be something which we will address upon quite soon. And one of the reasons it's studied quite a lot is that there are methods of solving these equations in some exact sense. Now, having said that, the simplification we made in both the equation, be the Euler's equation or the Stokes equations. In Euler's equation, when we said there are no viscous effects, and Stokes equation when we said there are no inertial effects, they are good description of many problems, but they rule out or they don't show up some very crucial phenomena in the problem that you're interested in. So, especially we will get introduced to that when we talk about Euler's equation at length. We will see that it leads to some severe flaws in terms of understanding forces on objects. So, that's a part which we will look into. But before we start discussing the equation, as you always would know, that solving any equation, just the differential equation by itself, cannot be done unless you specify the boundary conditions. Every differential equation would come with some kind of boundary condition. Without that boundary condition, the equation cannot be solved. So, you would need some boundary condition and some initial condition, because the Navier-Stokes equation, if I write that up again, so I am just writing it right now without the body force part. If you analyze this equation, this is an equation that is a first order equation in time, and it is an equation which is a second order equation in space. Now, there are various classifications we often do to PDEs. This is a partial differential equation. There are various kinds of classifications we are used to thinking of in terms of PDEs. The classification typically we go for are whether the equation is a hyperbolic PDE, a parabolic PDE, or an elliptic PDE. Now, the nature of Navier-Stokes equation is such that in different limiting scenarios it behaves as one of these kinds. So, the Stokes equation that I described a while back, which is basically completely ignoring the acceleration part, that has a nature which is elliptic of kind. The Euler's equation, which is completely ignoring the viscous part, that has a behavior which can start showing hyperbolic nature. And the full Navier-Stokes equation will basically go in between these regimes and also can show a parabolic behavior. So, with definiteness you will not be able to say whether the equation is of one of those kinds. So, based on the kind of problems that you are studying, it can show either of these behaviors. Now, the significance of trying to do this classification is that each of these kind of solutions would have certain kinds of nature of the solution. So, when you are solving an equation that is elliptic in nature, you need to prescribe boundary conditions everywhere. When you solve an equation which is parabolic in nature, you give an initial condition and then give the boundary condition. So, one classic example of a parabolic equation is heat equation, that when you are solving unsteady heat equation, you give what is the temperature profile at T equals to 0, and then given the boundary condition, you solve that heat equation. The hyperbolic equation, an example of this is a wave equation. So, there is a propagation of wave that actually, so you give an initial condition and that wave basically propagates and you see the initial condition distorting or traveling in time. So, a straightforward classification is not possible, you do it based on the problem that you are studying. But having said that, if you take the full Navier-Stokes equation, you know that you need to give an initial condition, but you also need to give boundary conditions. So, the boundary conditions that we have to consider first are problems which we will study quite frequently, which is when you have boundaries or as in walls. So, if you have flow that is happening either confined by two surfaces, I have drawn two parallel surfaces, they need not be parallel. So, you have two surfaces and there is a flow between them, or there is a flow past one particular surface. What is the appropriate boundary condition at a solid surface? So, what we need to now study is that what should be the boundary condition I'll keep abbreviating this here onwards with B and C. So what would be the appropriate boundary conditions at solid surfaces? So the first boundary condition that we will have is to say that a solid surface is impermeable. So that means that at the solid surface there is no mass flux. Fluid cannot penetrate through that particular surface. So if I define at any particular point a unit normal, which is n, and the velocity field in the fluid is u as a function of position and time, then the boundary condition on a solid surface is going to be u dot n is equal to 0. The normal component of the fluid velocity would be 0. So fluid, there would be no component of transport perpendicular to the surface. This is not, I've drawn two parallel straight lines as boundaries, but this can be for any kind of boundaries. You can have something which looks like this and it is equally applicable. The only difference is in the parallel case the normal remains the same everywhere. Here the normal is going to basically change depending on where you are. So whenever you are applying the boundary condition, so this is a boundary condition which is that is known as the no penetration boundary conditions. Now what if the boundary was moving? I take my hand and I move my hand, and obviously the air which is around it, it has to satisfy some boundary condition on my palm, and my palm is actually doing this back and forth motion. So what should be the boundary condition when the boundary itself is in a state of motion? So this is not too difficult because our boundary condition is motivated from mass conservation. It basically says there is no mass flow through the surface. Nothing can actually leak into the surface, which means this, if the boundary was moving, I'm going to modify this and write it as u wall dot n. If the wall had a velocity of its own, this would be the velocity of the wall. So this is the boundary condition which is very rigorously defined from first principles based on the fact that nothing goes through the surface. The surface is perfectly impermeable. Now if you were to solve a problem where you said, oh no, the surface actually has some kind of porosity, the surface you are having a flow over, let's say a sponge kind of a surface or something that is more porous in nature, then that has to be modified because you can now have some flow through that surface. But if you are looking at solid surfaces that are perfectly impermeable, there is no penetration of any liquid through it, then the boundary condition that you have is that the normal component of the fluid velocity should be equal to the normal component of the wall's velocity. If the wall was stationary, then that means that the normal component should be 0. The second boundary condition is not something that has such a strong conservation law basis. The second boundary condition says that if I look at a solid surface, I go back to the picture of the fluid actually being made up of molecules. Now these fluid molecules are getting transported. So let's say that you are trying to push fluid adjacent to a surface. As you try to push the fluid basically made up of these molecules are sliding over the surface. Now as it tries to slide over the surface, the boundary condition that we assume is to say that at the wall fluid is going to stick to the wall. So the fluid basically that is exactly attached to the layer of fluid molecule that is exactly attached to the wall, it has to stay stuck to the wall. So, this is what is known as a no slip boundary conditions. Now, how do we express this mathematically? So, if u dot n is the normal component of the velocity, then we know that the tangential component of velocity is going to be u dotted with delta minus nn. You can see this is an identity, right? U dot n multiplied by n is E plus, so if you see this term and this particular term, they are going to cancel each other. So, effectively this is another way of writing u. This component of u is the component of u which is perpendicular to the surface. This component of u is basically the component of u which is tangential to the surface. Think of it in terms of x, y, z. If the surface was on the xy plane and z was the normal, then this is basically uz z cap, and this one will actually give you ux x cap plus uy y cap. So, this particular operator delta minus nn, when it operates on any vector, it extracts out the component of the vector that is lying in a plane that is perpendicular to the vector n. So, it is a more compact notation because our surfaces are necessarily not going to be flat. Our surfaces can take any kind of shape. So, the tangential component is u dot del minus nn. This should be equal to the tangential component of the wall's velocity. So, you have the tangential component of the fluid velocity should match with the tangential component of the velocity of the wall. So, this is my no slip boundary condition. Now, obviously, if you combine the two boundary condition, you had a boundary condition where we said u dot n is equal to u wall dot n, and we had the tangential component and we had the normal component. If you combine the two, the boundary condition just says that the fluid velocity at any solid surface should be equal to the velocity of that surface. Now, this looks simpler than obviously what we have written down here, but the reason for splitting it in this way is because they come from different arguments. You can always say, I do not want to look into all these kind of tensorial decomposition of the velocity field and be happy with just saying u is equal to u wall, which is correct. If you have a boundary which is solid surface, that is no slip and no penetration, then the boundary condition is that the fluid velocity should be equal to the wall velocity. If the wall was stationary, then the fluid velocity, the velocity vector should be equal to 0. But it actually comes about from these two boundary conditions. One which is saying that there cannot be any penetration of fluid through a solid surface, and the other which actually comes from the fact that you would not have any slip over a surface. So, this decomposition is necessary because the boundary condition of no slip is not something that is guaranteed for every case. It is not guaranteed that we are going to always observe a no slip boundary condition, and this does not require you to do something very sophisticated. If you were to take leaf of a lotus leaf and put a drop of water, it will very nicely slide over the surface. So, it is clearly not sticking to the surface, right? Otherwise, it would not be possible for the drop to nicely slide over. So, there are various kinds of surfaces which are known as hydrophobic surfaces, where the fluid is not going to exactly stick to the surface. So, the fact that whether it is going to be no slip, so no slip is an approximation. You can again go back to how we have been discussing these things, that if you go to the molecular level, argue for this being an ideal gas made up of, which means if it's an ideal gas, it is basically made up of non-interacting molecules, you can show that no slip is the first level approximation you will get. So, when I say first level approximation, what it means is if you consider an ideal gas made up of gas molecules, every gas molecule travels a certain distance before it bumps into the next molecule. We have come across this term. This is known as the mean free path. How much distance would it travel before it hits a neighbor? And then you have a dimension here, which is the gap between, let's say, the two solid surfaces. So now you can automatically start to see. So let's say you have a channel, you are trying to push gas through that channel. So now if you ask the question that there is a parameter here which is the mean free path of that gas molecule divided by the system size. So obviously you expect that as the mean free path, or in other words, as the system size goes down and starts to become more and more comparable to the mean free path, the assumption of no slip is going to become a bit suspect. It's not guaranteed, because in the limit of where the system size becomes comparable to the mean free path, the molecules can basically hit the wall before it hits the next molecule. There is a possibility that collision, molecule-molecule collisions, can be interrupted by collision of molecule with the boundary. So effectively, when this quantity lambda by h becomes larger, your assumption of no slip is becoming a little dubious. So the no slip assumption is a very good assumption in the limit of lambda by h going to 0. And this quantity lambda by h is known as the Knudsen number. So when you do kinetic theory, when you treat all of these as molecules and try to arrive at your governing equation, you will also be arriving at your boundary condition. And the no slip boundary condition is the first order approximation, which means that there are corrections that you are going to get based on the mean free path. So what kind of corrections would you get? If you say that the system basically had some kind of a slip, it was not perfectly a no slip boundary condition. So we wrote down that the tangential component, I am using the symbol here to say this is the tangential component, is equal to u dotted with delta minus n or u minus u dot n. If this was perfectly no slip, then the tangential component should have been equal to that is what it should have been equal to. But if there is an amount of slip that is there in the problem, then the velocity at the wall, the tangential component, is going to disagree from the wall's tangential component. And if you do this from the kinetic theory point of view, it depends on the term that the disagreement is actually that depends on the shear stress. What is the wall shear stress? So the wall shear stress is basically going to be responsible for a deviation of the tangential velocity of the fluid from the wall's tangential velocity. So when you allow for some slip. Now how do we write this mathematically? Because finally we want to have a mathematical expression here. So to write this mathematically, you will have, we know that the component of the surface force is sigma dot n. That's the component of the surface force on any surface. Now we are interested in the component of surface force that lies on the surface. The shear force is a force that lies on the surface. So, to find the shear force on the surface, we go back to our favorite operator, which is delta minus Nn. So, delta minus Nn dot sigma dot n gives you the component of the surface force that is residing on the surface, because you keep seeing how this operator helps us, right? We are able to now write down an expression for the shear stress. Now, with the dimensional factor that takes care of it, mu is the viscosity and lambda has dimensions of length, which is known as the slip length. So, this quantity, this is the viscous part. So, we are looking at the shear stress here. So, no need to exactly specify because pressure does not have any shear component, but if you want, that is the viscous part which is going to contribute. So, you have now the tangential component of fluid velocity minus the tangential component of the wall velocity is going to be equal to the wall shear stress times a slip length. So, if I know that I am doing a Newtonian fluid, so for a Newtonian fluid, I have sigma is minus P delta plus 2 mu E. You can verify that delta, when I basically do this operation, delta minus Nn dot sigma dot n, as I wrote down here, the contribution from pressure, if I were to do this purely from pressure, that would be 0. So, the only part that is going to come in here is going to be 2 mu E. Pressure does not have any shear component, pressure will only have a normal component. So, this then becomes U dot n U wall minus U wall dot n plus 2 lambda delta minus Nn dot E dot n. Now, this I can just write using one single number, one single constant, lambda. So, that is my modified boundary condition at a wall, allowing for a slip. And seeing deviations from slip is not very uncommon. You can see for various reasons. It could either be you want to engineer a surface that has some kind of a slip. If you design a surface that is hydrophobic in nature, there can be. So, slip can come because of various reasons. So, one reason that I gave here, which is the more formal reason based on kinetic theory, is that your system size starts becoming comparable to your mean free path, which is why you are getting a slip. The other reason is where you have designed your surface such that the fluid has less affinity to be attached to the surface. So, that is the hydrophobic reason. So, primarily there are various ways by which you can argue for when slip deviations will occur. So, one is when system size starts to get comparable to the mean free path. So, this is basically saying decreasing dimensions or decreasing system size. The second reason, altering the physiochemical properties of the surface, which is one example being you are interested in patterned surfaces or textured surfaces where you have hydrophobic behavior. There is another example where this also applies, is that when you have flow past porous media. So, this one, instead of it actually just being a wall, is a porous media. So, you have, let us say, a porous bed which is there over which you have a flow. So, there you can again try to calculate what is the appropriate boundary condition at the porous media surface. And when you do that, I am not doing that derivation here, you will arrive at a boundary condition that the tangential velocity of the fluid on a surface that is the bounding surface of a porous media is not equal to the wall velocity. So let's say the wall was stationary, you would expect that the tangential velocity should be 0 if it was a no slip boundary condition. Turns out it is not 0. Turns out that if you were to look at the velocity for a porous media, the velocity can go further deep down, because here this is not perfectly a impermeable solid. So it can go a little bit deep down, and here at the wall, which is stationary, the fluid velocity has a certain slip. So this is the boundary, which is why I made this distinction between studying these boundary conditions separately. So now if you close the complete picture, your fluid velocity, so at solid surfaces, U is equal to, combining the normal and tangential component, is going to be equal to U wall plus a slip length delta minus Nn dotted with, for a Newtonian fluid, E dot n. In the limit of the slip length going to 0, you recover the boundary condition of no slip, no penetration. Otherwise, you will have no penetration, but the slip will be possible based on that value of slip length. And when you decide your n, you have to just pay attention that if you have two surfaces, this is the normal from the surface to the fluid. So if this was my z axis, the normal here is z hat. The normal here is minus z hat. So you have to be a little careful when you are applying these boundary condition on surfaces. You have to make sure that you are taking the appropriate normal. Okay, so this was all the story that we had for surfaces that are solid. So any flow past any solid surfaces, this is what you are going to get. Now fluid can also flow past surfaces that are deformable. So deformable surfaces are not something again very rare. Most physiological examples like your esophagus, your blood vessels, veins, arteries, everything is a deformable surface. So when there is a fluid going through that surface, the boundaries are or the tubes or the surfaces over which the flow is occurring is a deformable surface. But there is even a simpler example where you see deformable surface. The simple example is, if you have a glass of water, so this is water in a glass. So on the walls of the glass or the beaker, you have your classical no slip, no penetration boundary condition. Now if you give it a tap, all of you, without knowing any fluid mechanics, would observe that there are certain waves that would be generated on the surface of that water, which means this interface between air and water, or for that matter any two liquids, requires you to also think of another boundary condition. So that brings us to the part regarding interfacial boundary conditions. What happens? So I'll just draw a surface. So imagine this is my surface that is separating out two liquids. I have a liquid 1 here and I have a liquid 2 here. What should be the appropriate boundary condition on this surface? And I'm going to consider these two liquids to be immiscible. So whatever is below this surface stays there, whatever is above that surface stays there. There is no exchange that is going on, there is no miscibility that is going on. So in which case this boundary, so if I define this boundary as at z equals x, y and t, this boundary is an unknown of the problem, it is responding to the motion. As there is a flow that is being generated, which going back to that example of water in a beaker, that boundary itself, the shape of the boundary itself is an unknown in the problem. You obviously have velocity and pressure as unknowns, but you also have the interface height is also an unknown in the problem, and you need to solve for that. So this then poses the question that how do we go about actually finding this? Because now you need to know an information regarding how do the two fluids actually talk to each other. What is the mechanism by which these two fluids are going to interact? So for that, we are going to break the boundary condition into two pieces. The first one will have no connection to forces that are acting. There is nothing to do with any forces. So you have some surface that is basically separating out at z equals eta xy comma t, and this is an immiscible fluid. This is also non-reacting. Sometimes what you might have is between the two fluids, there might be a reaction that is going on. So this is a non-reacting immiscible system that you have in mind. So this boundary, this interface that you have is a material surface. We have encountered this terminology before. Material surface is a surface where if it is constituted of, if I draw points on these surfaces, or if I tag fluid parcels on these surfaces, they are going to stay on that surface and not leave that surface. That's the definition of a material surface. We did this exercise when we were also trying to look at conservation laws. So that interface between the two fluids is a material surface. And by definition, if something is a material surface, if I have any quantity is a material surface, that object will have its material derivative be 0. There will be no rate of change of that quantity. So in the Eulerian sense, it should be now here the material surface is the equation of that surface for me, z minus eta xy comma t. That is the equation. I am defining that surface by this function f, which is z minus eta x comma y comma t. So now when you apply it on this f, you will have dz dt minus dou eta dou t minus u dot del eta is equal to 0. The first one gives me the vertical velocity at the interface. So uz at the interface. So if I say my velocity components are, okay, I've been using I think uvw. So let me just uvw. So the vertical velocity at z equals eta is dou eta dou t plus u dot del eta, again obviously evaluated at the interface. Now, so this if you were to write it down, you have dou eta dou t plus u dou eta dou x plus v dou eta dou y. So the boundary condition, the kinematic boundary condition is that at z equals eta, I have w equal to dou eta dou t u dou eta dou x plus v dou eta dou y. Eta is that unknown variable and it is going to respond to the velocity at that interface. So now you can see that the fluid velocity is not 0 at the interface. Unlike a solid surface which was stationary, where we said that it is no penetration and no slip. Here the velocity at the interface, so what this says is w at the interface is the normal component of the velocity. So if there is a w at the interface, it is going to lead to a rate of change of the height of the interface at that location. But there is also going to be a contribution that will come in from the fact that if there is also tangential or horizontal velocities on the interface. So if there is a u velocity and a v velocity on the interface, that is also going to be responsible for the change of the interface height. So simple, if you think of it, that at every point, if there is a w and there was no u and v, the interface is just going to go up. There is going to be a change in the interface. but the interface at some places, because if the interface just continuously keeps going up, that is going to violate mass conservation. Because if I have the interface rising everywhere, that means I'm increasing the volume. So that is going to violate my mass conservation when I'm thinking of an incompressible system. So when I'm thinking of an incompressible system, then the interface will rise at some location and it will fall at some other location. So if there is a vertical velocity at different points on the interface, it will come with additional horizontal velocities, which is going to be responsible for the evolution of the interface. So this is a kinematic boundary condition that you need to apply at the interface. So we saw about the kinematic boundary condition. The kinematic boundary condition basically gives us how the interface, which is an evolving surface, responds to the fluid velocities at that location. Now, since the kinematic boundary condition is relating only the motion of the interface to the velocity, we need additional boundary condition which tells us how the velocities at the interface are related to the forces. Or rather, if I have an interface, there is a fluid which is on one side of that interface and there is another fluid on the other side of the interface. The question is that the velocity, pressure and thus the stress on the fluid which is occupying the region 2 and the velocity, pressure and thus the total stress occupied at in the region 1, how do they talk to each other at the interface? Because the interface is basically a boundary between two liquids, and what we are assuming here that the liquids are immiscible. They are immiscible, there is no reaction that is going on at the interface. So you have a scenario which would be reasonably good for thinking of air, water or oil and water. You're thinking of a case where the fluid from region 2 is not going and mixing with region 1. They are well segregated. And the question is, how do we understand the force balance at the interface? So just like any force balance that we have been doing, if you blow up a region of the interface, you try to ask the question that if I were to consider a circuit, so I have drawn a contour here. So this is a contour line that I have drawn at a particular patch. So I have an interface, I considered a small patch at the interface. If I want to do a force balance, what is it that is so special about the interface that is different from any other surface that is in the bulk? So let's say in the region 1, I draw a fluid surface. Similarly, in region 2, I draw a fluid surface. What is so unique about region 1 and 2's boundary compared to any other surface that is embedded entirely in region 1 or region 2? And the answer basically lies in the fact that at the interface, you would have molecules. So if I draw a shaded molecule belonging to region 1, the molecule which is in region 1 is surrounded by similar neighbors, but also surrounded by dissimilar neighbors. So these are molecules from region 2 and region 1. If you now contrast this with one of its other members in region 1, they are purely surrounded by region 1 molecules. So what this does is the affinity or the interaction that we spoke about, which was basically in terms of the van der Waals attraction that this molecule is experiencing. So this molecule has a net attraction that it experiences from the other molecules. So the other molecules are basically pulling it towards itself. That is dissimilar. I'm just drawing different length arrows here. They are dissimilar for the molecule which resides at the interface compared to the molecule that resides at the bulk. So when you are trying to calculate the free energy of the interface, there is going to be a force that would be there because of this aspect of disparity in the interactions. So the van der Waals interaction that it gets, so you can think of the entire system being made up of two kinds of molecules, let's say air molecules and water molecules. And then the guy who is sitting at the interface, it's surrounded by air molecules on one side and water molecules on the other side. So effectively there is a difference in this interaction, and from that if I try to actually go about calculating, I would get a force that sits at the interface. So there is a force which is the surface tension force, and this surface tension force is basically present at the interface. Now what is it like? So if you think of a tent, and you are trying to basically have the tent, so the tent has a pole and you are trying to basically set this tent up. So what do? You tie a bunch of ropes, right? So you have these pegs which are put on the ground and you have these ropes connected to the tent. So what these ropes are doing, they are basically pulling the tent and keeping it in that shape that you want. So surface tension acts in a very similar manner. So at this contour, so imagine you have a surface, I have drawn this contour. At this particular contour, you are going to have a normal. So the normal is basically pointing out of that surface. There is a tangent that is there. These are all vectors to the contour. And then there is one more normal that is residing on the interface but is perpendicular to the curve. When you think of any curve on a surface, on that particular curve, there is going to be a normal to that surface, there is going to be a tangent which will be along that curve, and then you can have the third component of that orthogonal system. So there is this one vector which is pointing normal to that curve or that line that sits on that surface, and surface tension forces are going to be directed along that direction. So this is the surface tension force. If I consider a small line element, then the surface tension force would be the surface tension coefficient gamma directed along that particular direction which is perpendicular to that line sitting on the interface and that line element. So now if you go back to your Navier-Stokes equation and you try to actually calculate what is your, so you construct a small volume that is basically sandwiching or including that interface. So you will be integrating So this is what would happen, right? You have the acceleration integrated over that volume, you have the integration of the surface force or the surface stress tensor over the surface area, and then you have an integration of the surface tension that is basically acting on any contour that is defining that particular surface. So now if you were to shrink this volume, this is basically the same trick we use in every problem. We design a volume, and then if we keep shrinking the dimension of that particular volume, this object, the contribution from the acceleration is going to vanish. And what would survive is basically a competition between the surface stress and that from the surface tension. This is basically what will survive. When we did this in the bulk, then it was only the surface stress that survived. And we effectively ended up getting a relation for what was the expression for the stress tensor in terms of the surface force. That is basically how we defined it. Now when you are doing it at an interface, there is going to be a surface, the surface force is going to be defined in terms of what you have in terms of the surface tension. Now this part, the part which is this gamma S dl, this is an integration over the contour C that I have written down, which is bounding that surface. Now there is a bit of algebra that follows from here. You use the version of Stokes theorem in terms of converting this line integral to a surface integral. So I'll directly skip over what that exact the steps involved in that integration is. You can look up how we go through the steps going from the line integral to the surface integral. So directly writing out in terms of a surface integral, you get this relation. Now, I will explain what these quantities are. Gamma is obviously the surface tension coefficient. As you can already see, this has units of Newton per meter. It is force per unit length. N is the unit normal to the surface. Del S, it is a gradient, but it is not any gradient. Del S is basically gradient minus N dot del. Now, what do you think it is? N dot del is the component of your gradient that is along the normal. When you take gradient, you take a gradient and you basically dot it with some vector, you are extracting the derivative along that particular direction. Z cap dot del is nothing but dou z. X cap dot del is nothing but dou x. Similarly, N dot del is the gradient or the derivative which is pointed in the normal direction. When I multiply this with N, I basically get a vectorial quantity. So, x cap into x cap dot del is basically x cap dou x. So, from the del operator, we are taking out the part which is giving you the variation in the x direction. Now, when I subtract that from del, it gives me the component of the derivative which lies on the surface that is perpendicular to N. You can see this quite easily if you do it in a plane surface. In a plane surface, the normal is in the z direction. So, then I will have del minus z cap dot del. So, if you simplify, this is x cap dou x plus y cap dou y plus z cap dou z, and then you have z cap dou z. So, what you are left with is the part of the gradient that resides on that surface. So, this is a surface gradient. Del is just a gradient, but del S, which is defined in this way, is a gradient that is taken on the surface. So, for planar problems, it is quite easy to understand that it is a two-dimensional version of the gradient. But the surfaces need not be planar, the surfaces can have any arbitrary curvature, in which case when you do this operation, you are extracting, you are looking at rate of change of quantity spatially, but always doing that variation on a surface. There is no variation that you are interested in that is perpendicular to the surface. That is the whole idea of this particular quantity. So, with that, now you have this particular part. Now, sigma dot n ds, this quantity, this is done over the surface. So, it will have two contributions from this. So, this will have, when you are calculating this, it will have an n dot sigma from the bottom, and it will have an n dot sigma from the top. Now, here you have to realize I have made an error here. The error is the n dot for both are not the same. The n dot sigma from the bottom is basically the normal that is pointing from region 1 to region 2. So, this should actually be n1, whereas for sigma 2, it is the normal that is pointing from region 2 to region 1. So, what I had here was the normal pointing from region 2 to region 1 is minus n1, and I had written this as n. So, in which case it is going to be n dotted with sigma 2 minus sigma 1. So, this now kind of closes the story. So, you have n dot sigma 2 minus sigma 1 plus del S gamma minus n gamma del dot n ds is equal to 0. That is the force balance on the surface in the limit of the surface becoming infinitesimally thin. You construct a, so you have a surface, you construct a control volume, you shrink this dimension. You shrink this dimension and basically bring it to the surface. So there is going to be a surface force contribution from the top, there is going to be a surface force contribution from the bottom, and there is a force that is residing at that on that line. The contribution from the acceleration is going to vanish. So finally you would arrive at this relation. Now this should be true irrespective of what I choose. So in the as a limiting process, this again goes back to how we have been doing this. It gives me an expression that I now have the following as my dynamic boundary condition. Now this in this particular form is not very easy to understand what is going on. So it gives me a jump in the surface force expressed in terms of surface gradients of surface tension, and then del dot n is my curvature. So what I will do is I will split this force balance, because finally what you have on each of these terms are forces. Everything is an order 1 tensor, everything is a force here. So what we will do is we will try to actually do balances for the force, one in the normal direction and the other in the tangential direction to the surface. So to do a balance in the normal direction, what we do is we take the force balance that we have. So this you can think of as summation of forces is equal to 0. Force per unit area. So this is basically summation of force per unit area is equal to 0. So what we will do is, in order to look at the balance, one along the normal and the other basically perpendicular to the normal, we dot this expression with n. We take a dot product with n for this expression. So the first term becomes n dot sigma 2 minus sigma 1 dot n. The second term is the surface gradient dotted with n, and the last term is n dot n gamma del dot n is equal to 0. Now n dot n is 1. This quantity is del S gamma dotted with n. Now we said del S is a surface gradient, so that is gradient minus n dot del. So if you dot this with n, you will have n dot del n dot n, which is n dot del minus n dot del, and that is 0. And that is expected, because del S is the gradient which is lying on the surface. When you dot it with the normal, obviously it will be 0. You have a gradient, a surface gradient, let us say x cap dou dou x plus y cap dou dou y. If you dot it with z vector, you are going to get 0. That is exactly what has happened here. So this term will go to 0. Here n dot n is 0. So finally you have a surface normal stress balance, which tells us that sigma 2 minus sigma 1 n dot double dotted with n is equal to gamma del dot n, and del dot n, as I said, is the curvature. If you take any surface, any arbitrary surface, the curvature will depend on, so any surface will have two radius of curvature. So let us say this has R1 and this is R2 at any point. So the curvature would be 1 plus R1, 1 plus R2. If you have a sphere, then R1 is equal to R2 is equal to R, and so the curvature is 2 by R. If you have a cylinder, R1 is equal to R and other radius is infinite. There is only one radius of curvature, the other one has been pushed to infinity. So in which case the curvature is 1 over R. if you have a planar surface, then R1 is equal to R2, both have been pushed to infinity, in which case the curvature is as expected 0. So, you can find it for any surface. I just took 3 surfaces, but for any surface you can define what the curvature is. So, now for a Newtonian fluid, sigma is minus P delta plus 2 mu E. So, the normal stress balance is going to have P1 minus P2 plus 2 n dot mu E. So, I have this is mu 2 E2 minus mu 1 E1. So, you will have a jump in pressure and you will have a jump in the normal viscous stress, which will be balanced by surface tension and the curvature. So, which tells us even if it is a static problem, if you have a static problem, there is no motion, you can still have a jump in pressure between the pressure inside and the pressure outside, which will depend on this, which is typically what we know about bubbles, drops, etc., that you can have it in a static state, it can maintain a spherical shape because of surface tension. The pressure inside is different than pressure outside, and that is enabled by the fact that you have surface tension in the problem. The tangential one would require us to go back to our equation, which was sigma dot n plus grad s gamma, and then we had minus n gamma del dot n. Now, for this, what we will do is we will take a dot product of this, instead of with the normal, we will take a dot product with a tangent vector. So, the tangent vector, if I define on the surface, would be some constant s plus some constant b. If you remember from our sketch earlier, that on the surface at any point you have these two perpendiculars. One is along that contour b, and then there is the other which is perpendicular to that. So, you can define the surface tangent using these two vectors. So, you have a tangent vector. So, I will dot with this with the tangent vector sigma. So, this is the jump in sigma dot n, and then I have the tangent vector dotted with the surface gradient and the tangent vector dotted with the unit normal gamma del dot n is equal to 0. Now, this by definition is 0, because the tangent vector is normal, is perpendicular to the unit normal. So, that is 0. And here, if you explore this particular term, use a Newtonian fluid as your example right now. So, for a Newtonian fluid, T dot sigma dot n, this will only have a contribution from the viscous part. There will be no contribution from the part due to pressure. So, you will have 2 mu 2 E 2 mu 1 E 1 dot n is equal to minus grad s gamma dot the tangent vector. So, this part is going to extract the shear stress in the problem, the viscous part or the shear stress in the problem. So, there can be a jump in shear stress between the two fluids. What allows for that jump is gradients of surface tension. So, you can have discontinuity of shear stress if there are gradients of surface tension. So, one simple way of doing that is surface tension depends on temperature. So, if you were to heat the system, on the surface there are different kinds of location where it is getting heated and somewhere it is cooled. So, you have an interface. So, think of this particular problem. The interface is perfectly flat, right? The interface is flat implies that curvature is 0, which means in this particular scenario, you will not have any surface tension contribution in the normal stress problem, because I have a perfectly flat interface. But let us say that I have temperature here is higher than the temperature on the right hand side, which means again if I think in terms of surface tension, the surface tension at this location is going to be higher than the surface tension in the cooler location. If I have a fluid where surface tension basically is either, so in this case if I am heating it, so this should be lower actually, yeah. So, I am basically considering a scenario where surface tension gets lowered with increase in temperature. So, the surface tension here is going to be lower than the cooled end. So, in which case with the decrease in surface tension you have a gradient. If you think of it just as a two-dimensional problem, you have a dou gamma dou x, which is negative, and this is going to allow for a jump in shear stress between the two fluids. So, these problems are known as Marangoni flows or Marangoni problems, where you have a possibility of surface tension gradients that will drive a flow or that will allow for a shear stress discontinuity. If surface tension was a constant everywhere in the fluid, then this term would be 0. If at the interface at every point surface tension is a constant, then it becomes identically 0. And then your shear stress should be continuous across the interface. So, that is the summary of the boundary conditions, because in fluid mechanics problems we are not always going to solve problems past a surface. You will do multi-phase problems, you will do problems which are interfacial in nature, and in those cases you need to know what are the boundary conditions that you need to use. For instance, again, like if you one way to have the surface tension gradient is if you have surfactants. So, if there are these, if you think of again a drop, and this is what typically you will see encounter in detergents, if there are these micelles which are going and accumulating in one part of the drop, they are going to alter the surface tension in that part of the drop compared to the remaining part. So, now you have surface tension gradients that are being set up by these micelles which are lowering the surface tension, and so you are going to get a flow, or in first case you are going to get a shear stress discontinuity. The shear stress need not be continuous. So, we learnt about boundary conditions at a wall, no penetration, no slip. We also saw that no slip is an approximation, it breaks down in certain scenarios, in which case you allow for a slip boundary condition. Then when you have an interfacial problem, you are going to encounter boundary conditions which are first kinematic. So, kinematic boundary condition says the interface is a material surface. Because it is a material surface, the velocity at the interface are related to the evolution of the interface. If you have an interface given by a coordinate, then that evolution of that coordinate is tied to the fluid velocity at the interface. And then you applied the dynamic boundary conditions, which would be a normal stress and a tangential stress boundary condition. This closes the system of boundary condition. Now, when you have these boundary conditions, you can go ahead and solve any problem, whether you do it by hand or you do it in a computer. You can take your governing equations and use these boundary conditions to solve any problem. That is the need for knowing these boundary conditions. Okay.